In this video, we're going to derive the minimum angle required to slide down an incline. Basically, the minimum incline angle to require to slide down this incline. And this incline has friction, all right? We're going to say that the mass of this block is m, our incline angle is theta, and since we have an incline with friction, we're going to say that we have a coefficient of static friction, okay? So a coefficient of static friction for this incline. And basically, because this block is undergoing static friction, meaning this block, it isn't going to move. It's just going to stay where it is. So basically, these are the three things that we were given, right? We were given m, theta, any coefficient of static friction, mu s. Now, the block isn't going to slide down the incline because of static friction. But if we were to increase the angle of incline, then eventually this block would be at such a high angle of incline that will eventually slide down, right? And so what is the minimum angle required to make this block slide down the incline? That's basically what we're going to figure out. How do we do that? Well, we know about the forces acting on a block on an incline. We, of course, know about the weight force. That's going to act directly downwards. So we're going to say that's mg. And, of course, the normal force acting perpendicular to the surface. So that would be our normal force. And we also have static friction. So we do have a static frictional force acting this way because, remember, the block wants to move down the incline because its weight wants to pull it or push it or pretty much bring it down the incline. So static friction has to act in the opposite direction of where it wants to move, which is that way. And so this would be static friction. So this is basically the forces acting on our block. And basically, remember what we like to do. We like to break up our weight into components like this, right? We like to break it up into components, right? We like to call this the x direction and this the y direction. And so we know that this component of the weight force, so the y component of the weight force here, we know that this is just mg cosine theta, right? So mg cosine theta, and this one's just mg sine theta. So remember, the block isn't going to move. So the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction also equals 0, right? And pretty much based on the forces that we're given, we know what these forces in the x and y direction are. In the x direction, it's just going to be mg sine theta minus fs. Right, that equals 0. In the y direction, we have fn minus mg cosine theta. Okay, so basically if these are true, then that means fs is equal to mg sine theta and fn equals mg cosine theta. Now remember, what equation do we use? I mean, what are we supposed to do? Well, remember, our goal, right, we want to find the minimum angle, all right? So basically, I'm going to write what we have to find right here. Right, we want to find the minimum angle required to slide down the incline. So we're going to find theta min. Now, theta min, right, the minimum angle is dictated by the maximum static frictional force. Right? If you recall, static friction, right? Static friction, we could write it right here actually. Static friction is less than or equal to mu s Fn. Pretty much because the static frictional force acting on a block is always less than or equal to the maximum static frictional force. So the maximum static frictional force, we know, is just equal to mu s Fn. And so hopefully this idea makes sense, where if our static frictional force is less than or equal to some value, mu s Fn, which we know that's what it is, then our maximum possible value for the static frictional force is going to be equal to that value that it's less than or equal to, basically. So this would be the maximum static frictional force. And so since we want to find the minimum angle, that means we have to involve the maximum static frictional force. And so we're going to replace Fs with the maximum static frictional force that we could have, which is mu s Fn. And so really we have mu s Fn equals mg sine theta. And remember, this is our maximum static frictional force, then it's the minimum angle required to make this block slide, right? So now we're going to solve for theta min, right? Now we also know that the normal force is equal to mg cosine theta. So we just write mg cosine theta for the normal force. So really we have mu s mg cosine theta. That's equal to mg's. Okay, this is, remember, now we're dealing with the minimum angle. So this is now going to be the minimum angle, right? And it's equal to mg sine theta min. All right, and notice how mg will cancel out on both sides because it's will cancel out on both sides of the equation. And so we're left with mu s cosine theta min equals sine theta min. So now this is basically the equation that we're solving. Notice how we can divide cosine theta min on both sides. And the reason why this works is because, of course, we know this cancels out and we're left with mu s. But really, what's this? Sine over cosine is just tangent, so we get tangent of theta min. And so as a result, we used to solve for theta min. Theta min is really the tan negative 1 of the coefficient of static friction. And so this right here would be the minimum angle required for this block to slide down the incline, right? We're given coefficient of static friction. And that's the whole idea of how it works. Basically, it's the idea you gotta apply maximum static frictional force to it because maximum static frictional force is what dictates the minimum angle required to slide down. And so we see that it doesn't depend on the mass of the block. It only depends on our coefficient of static friction. And so we see that it's the tan negative 1 of mu s. And that's basically the idea. That's pretty much it.